In this video, we're going to be proving that quadrilaterals are parallelograms. In a way, what we're going to be doing is the exact opposite of what we did in the last video. Okay, we're going to start with a quadrilateral that has certain properties to it, and we want to show that it is, in fact, a parallelogram. And to show that a quadrilateral is a parallelogram, what you really need to do is show that its definition is present, which is that the opposite sides are parallel. Okay, so we'll be given some properties. Using those properties, we'll show that the opposite sides are parallel. Most of the examples that we're going to do here are going to appear to be the converse of the proofs that we did in the last video. For example 1, we're going to prove that if the opposite sides of a quadrilateral are congruent, then it is a parallelogram. Okay, this is a converse statement of something we did in the last video, which was if you had a parallelogram, the opposite sides would be congruent. All right, so we're going to be working backwards to show that the top and the bottom are parallel and the left and the right are parallel. All right, so let's go ahead and start by labeling our parallelogram. Let's go ahead and just call this ABCD. We'll just go ahead and call it ABCD. And our given information would be that AB is congruent, AB is going to be congruent to CD. I'm going to write that backwards on purpose. And AD is going to be congruent to CB. Okay, and that is given. That is our prompt to the problem here. In the picture, we can go ahead and label that. Go ahead and put single markings and double markings. Step 2, a lot like what we did in the last video, we're going to go ahead and add in a diagonal. Okay, let's say that we draw, we'll do DB. All right, so given that segment, step 3, we can state that DB is congruent to BD, again, backwards for a reason here. We can state that using the reflexive property. And if you put all these things together that I've got so far, we actually have side, side, side. We have the side, side, side shortcut here that can show us the top and the bottom triangles are congruent. Okay, so for the top, let's go with ABD. Okay, so then the bottom is going to be CDB. And that would be side, side, side. So, corresponding parts are going to be congruent. In particular, 1 and 2, those two angles are going to be congruent. Okay, they sit between the single mark and the reflexive side. And 3 and 4 will also be congruent. Those sit between the double mark and the reflexive side. Okay, so angle 1 is congruent to angle 2. 3 and 4, and that is CP, CTC. Okay, and what that tells us, that actually gets us to the very end here. It tells us that AB is going to be parallel to DC, and AD and BC are parallel. Reason for that is going to be AIA, alternate interior angles. Okay, angles 1 and 2 fit the definition of AIA. You get that Z shape here, transversal in a couple of lines. If they happen to be congruent, which is what we get from CPCTC, that tells us that the top and the bottom will be parallel. AD and BC are going to be parallel because of 3 and 4. Those fit the definition of alternate interior angles as well, because you've got that transversal here. You also have those two sides. And technically, we do have one last step that we should write. 7, we can say that ABCD is a parallelogram. And the reason is because the definition of a parallelogram. The definition tells us that the opposite sides are parallel, which is what line 6 tells us. For example 2, we're going to prove that if the opposite sides of a quadrilateral are congruent, then it is a parallelogram. All right, so let's go ahead and label up our parallelogram here. Let's go ahead and call it ABCD. Okay, and our given information would be this, that angle A is congruent to angle C, and angle B is congruent to D. That would be our given. That'd be our given information. All right, so then what we're going to need to do is change it so that it says that the measurements are equal. So line 2, the measure of angle A is equal to the measure of angle C. The measure of angle B is equal to the measure of angle D. That would be the definition of congruent angles. All right, and now that we have it in this form, what we can start doing is adding angles together. Okay, and remember, this is a quadrilateral. All right, not going to get this to fit in one line, but the measures of angles A, B, C, and D, all the angles, are going to equal 360 degrees. Actually, for space, I'm just going to move it over here. I'm going to put it on this side. Might look a little bit messy, but that's all right. Okay, it's going to equal 360 degrees because quadrilaterals equal 360. You can call it the polygon sum. And because of what we have up here in line 2, we can use some substitution. Angle C can be substituted with angle A. Angle D can be substituted with angle B, which would give us an A, a B, an A, and a B, equal to 360, which we can all group together as 2 times the measure of angle A plus 2 times the measure of angle B is equal to 360 degrees. Okay, so I did a couple of things there. We used substitution, and at the same time, I went ahead and combined like terms. So we'll just let that be in the same step. Okay, and then for 5, I can divide everything by 2. The measure of angle A plus the measure of angle B is going to equal 180 degrees if you divide everything by 2. So division property of equality. And what's special here is that these are now supplements, that A and B are supplements. And if you go back to the picture, A and B are consecutive interior angles with respect to AD and BC. So that tells us, because they're supplements, that AD must be parallel to BC. That would be consecutive interior angles. Because the consecutive interior angles are supplements, these two have to be parallel. All right, as far as the top and the bottom, what we'll write, we'll go ahead and write that AB is parallel to DC, and just as your reason, we can write same argument. Let's spell that correctly there. It would be the same argument that we have. In other words, what you do is just show that maybe A and D would be supplements, which would mean that the top and the bottom are parallel. All right, example 3, we're going to prove that if the diagonals of a quadrilateral bisect each other, then it is a parallelogram. All right, so let's go ahead and add in some diagonals here. Okay, so we've got that one, and we've got this one here. And what we should probably go ahead and do here is label the quadrilateral. Let's go ahead and go with ABCD again. The point of intersection, we'll go ahead and call that point P. The This might get in the way of some other things. I'm gonna try and write it here and see if I can work around that spot there, but that's gonna be point P in that location. All right, so for the very first step, what I could do is write down that I'm gonna draw the diagonals in there, okay? But the proof is gonna be a little bit lengthier, so I'm gonna go ahead and leave that out and just let that be part of the given information in a way. And what I'm gonna start with is the statement here that the diagonals bisect each other, okay? So I'm gonna write down that AP is congruent, this piece right here is gonna be congruent to CP, and at the same time, I'll write down that DP is congruent to BP. Okay, and that is our given information here. Okay, the prompt to this is that the diagonals bisect each other. So then those parts would be congruent, in which case we should go ahead and add in some markings to indicate that that is true. Okay, step 2. And keep in mind here that the goal is to prove that this is a parallelogram. So we need to show that the top and the bottom are parallel, the left and the right are also parallel. Okay, so back to step 2 here. I'm going to introduce some angles. I'm going to call this angle 1, this angle 2. So it's right there next to the P, but this will be angle 2. I'm going to call that 3, call that 4. So we got a lot going on in the middle there. But angle 1 is congruent to angle 2, these two. And angle 3 is congruent to angle 4, left and right, because those are vertical angles. And once I show that, if you take a step back and you look at this, you're gonna realize that we have enough congruence markings in different places to prove that certain triangles are congruent. Like the top and the bottom, those are gonna be congruent by side, angle, side. Okay, you've got that single, you got the double, and then 1 and 2 are the same size. So you have side, angle, side. The same thing is gonna happen on the left and the right. You're gonna have a side, angle, side, side, angle, side. Of course, these two triangles are gonna be a different size. Most likely they're a different size than the top and the bottom because 1 and 3 are not guaranteed. It's just that the vertical angles, those opposite angles are congruent. Okay, but we can go ahead and write down now that we do have these pairs of congruent triangles. Okay, so let's say the top one, ABP. Okay, so we'll go with that, ABP. That is going to be congruent to CDP. Okay, and likewise, ADP. Okay, ADP is going to be congruent to CBP. Reason for that will be side, angle, side. So those are all the bisected parts of the diagonals with the vertical angles that sit in between them. And if those are congruent, then any of the corresponding parts of those certain triangles would be congruent. So I'm going to label a few more angles here. I'm going to call that 5, that's 6. And these two will be congruent by CP/CTC between the top and the bottom triangles. Likewise, let's call this 7. Let's call that 8. And those will be congruent by CP/CTC as well, but between these two triangles. Okay, so for 4, let's list all that. That was 5 and 6. And 7 and 8. Reason is CP/CTC. Okay, and this is a little bit complicated to follow because we're working two triangles at the same time. But what's special about these angles that have been identified is that they fit the definition of alternate interior angles. If you look for that Z shape here, that 5 and 6, those are alternate interior angles. The 7 and the 8, you got that Z shape on the side here, but they're going to be alternate interior angles between the left and the right side of the quadrilateral. Okay, so for 5, we can go ahead and use those alternate interior angles to prove that the opposite sides will be parallel. So the 5 and the 6, those two together are going to show that AB is parallel to DC. And 7 and 8 are going to show us that AD is parallel to BC. That is using alternate interior angles. Because the alternate interior angles are congruent, the sides have to be parallel. And 6, that means that ABCD is a parallelogram because we fit the definition of a parallelogram. And just as a little note here, if you go back to example 2, at the very end of that, I did not write what I have here for line 6, which is that it is a parallelogram. I actually just stopped at that part. So I think once we do reach that definition, we can conclude that it is parallelogram. So in example 2, if you want to go back and add that last line on there, you could do that. But if you don't, the idea is still there. These are parallel. All right, example 4, one last one to do here. Prove that if one pair of sides of quadrilateral are parallel and congruent, then it will be a parallelogram. Okay, let's go ahead and label some things here. We'll call it ABCD. Let's be consistent with that. The given information is that one pair of sides will be congruent and parallel. That parallel part actually tells us half of the problem is sort of done, right? Okay, let's go ahead and use the top and the bottom for the sides that they're referencing. Okay, so they're going to be congruent, so some congruent markings. They are also parallel. So we're already halfway done in a sense because the top and the bottom are parallel to each other. What we really need to do is prove that AD is parallel to BC, and that will conclude everything here. All right, now for this one, step 1, I am going to write down that I'm going to draw a diagonal. Okay, so I want to draw DB, okay? All right, so in the last proof, I left out that drawing part because it was part of the given in a way, because it did refer to the diagonals, but I'm adding this in here. All right, for step 2, let's go ahead and list our given information, things that we know here. We know that AB is parallel to DC. And I'm going to go ahead and group this up, even though it's a different type of a given piece of information. Go ahead and write down that AB is congruent. And here I am going to write it backwards because it'll make a little bit more sense overall. Okay, and all that is your given. So there are two different ideas, but I'm going to go ahead and just list them together here, just to go ahead and write them down. 3, because the top and the bottom are parallel to each other, that means that we have a couple of alternate interior angles in the picture that would be congruent. Okay, so I'm going to use AIA with the fact that we have parallel lines this time to show that the angles are congruent. And those angles are going to be right here. We're going to call that 1 and 2. So there's that Z shape that we've got. Okay, so angle 1 is congruent to angle 2 by AIA. All right, 4, that diagonal is congruent to itself. Okay, I'm going to call it BD for the top one. BD is congruent to DB. That is the reflexive property. Let's just add a little markings on there, just so there's something there. All right, reflexive property. And given all that information that we have so far, we've got the two sides, top and bottom. We've got the included angles. We also have the shared side. So by side angle side, we can prove that the top triangle and the bottom triangle are congruent. Okay, we'll call that ABD is congruent to CDB. There's your reason. Side angle side. All right, so if they are congruent, then we can say anything else is congruent that we want to that has not already been said, right? Like A is congruent to C, this angle right here is congruent to that angle, AD is congruent to BC. You could do that. But if our goal here is to really show that AD is parallel to BC, what we're really going to want to do is focus on these two angles here. We'll go ahead and call them 3 and 4. Okay, so line 6, angle 3 is congruent to angle 4 by CPCTC. And if these are congruent, and you see that Z shape here that we've got, if they're congruent and they fit the definition of alternate interior angles, we can conclude that AD is parallel to BC. And that'll get us to our parallelogram. But like in example 3, I'm going to go ahead and add that last little statement here, that ABCD is a parallelogram because of the definition of a parallelogram, which of course is that opposite sides are parallel.
Later, blah.